Hello again, and today we're going to have some fun. By saying having fun, I mean that we are going to practice our speaking English skills. In other words, English for specific purposes is our main target in today's class. I mean to say that today we're going to apply our speaking skills in order to get correct answers for some chemical kinetics problems. Um, yeah, okay, and we should start from the very beginning. I wouldn't say I wouldn't say that we are going to start from the ABC, from the foundation of chemical kinetics, and it's a good thing to do, I guess. And for your consideration, I have prepared a few problems. The first problem consists of two parts. And for that reason, you can see two tables on the screen of your computers, table A and table B. They are related to one another because they both are uh, based on the same reaction where the reagent A turns to two products B and C. And looking at the first table, we can see that four experiments were carried out, and the results the findings of these four experiments are put into this table, were put into this table. We can see that the third line of this table contains the information related to the value of the rate of this reaction. But we should bear in mind this factor, 10 raised to 5. That means that this value should be divided by this factor, okay? And the measurement units of this rate are is mole over liter per minute. Yeah. Now, also, it's natural that the value, the magnitude of the rate depends on the amount of the concentration of the reagent A. And again, we pay attention to the factor. It is 100, which means that in actual calculations, we should divide these values by this factor. Okay. Now, in the first in the first part of this assignment, they ask us to determine the rate of this reaction. Okay. Now, in order to get the rate of the reaction, we should uh, recollect the main law of chemical kinetics, right? And mathematically, we can write that it is, let me start writing here, okay? So W is the velocity, okay, is equal to K, which is the constant of the rate, the rate constant of this reaction, times the concentration of the reagent A raised to N, okay? And we are supposed to find the value of this N. Okay, how can we do that? Actually easy. We can do it easily. We've got the value um, of the rate of this reaction found in the first experiment. Let's write it this way, that W1, and this rate was found at the concentration of not 0.5. For that reason, we can write that W1 is equal K times 0.5. Remember about this factor times N, okay? Yeah, and that equals 0.3 times 10 raised to minus 5. Okay, this is the first reaction. Now, let's take a look at the data given in the second column related to the second experiment. The findings of the second experiment gives us the following picture. So it's K times, this time the concentration is equal to 3.80 times 10 raised to minus 2. Yes, and oh, I'm sorry. Yeah, I'm sorry. That's my fault. I have confused these two. The concentration is 1.78. Okay, so it's a similar expression. Yeah, the second expression. Now, what should we do is to divide the second equation by the first equation, term by term. Let's write it. 10 times 1.78 times 10 raised to minus 2, and this whole raised to n is equal to 3.8 times 10 raised to minus 5, right? And we divide it by k 0.5. Yeah, same expression of 3. That's it. That's it. And so finally, we got the following: 1.78 over 0.5 raised to n is equal to 3.8 over 3.3. Okay, so let me take a calculator. So 1.78 divided by is equal to 3.56. 56 n is equal to 3.8 over 0.3. We got that would be okay. In this case, in order to get n, we take a logarithm. Let it be a natural logarithm of the both sides of this equation. Right. In this case, n goes before the natural logarithm, and n equals natural logarithm of 12.67 divided by natural logarithm of 3.86, and it means 2.39 over 1 and 270. Okay, and that gives us please. Yeah, 1 and 999. If we round off, so we got 2. Yeah, we can see that um, the data given in the second column related to the findings obtained after carrying out experiment number 1. So they show us that the rate of this equation is equal to 2. It means that write, we can write the Kinetics equation for this reaction the following way. So the rate of the reaction is equal to K times concentration of reagent A squared. That's it. You may ask me why am I not calculating N for the other three experiments 0? So you can do that. You can do it on your own, and you will get 2 as well. I mean to say that I haven't got enough space on the screen of my computer to show you all these calculations, but they are absolutely similar to these ones. And in the long run, you will get the same value of the rate. n equals 2. Okay, so we got it. We have answered the first question of this problem, where they ask us to work out the kinetics equation for this reaction. In other words, we have got the value of the rate of this reaction, which is equal to 2. Okay, now in the second part of this problem, they ask us to confirm that these findings, the data contained in the second table, are consistent with what we have just found out. And we have just found out that the rate of this reaction is the second. Now, in order to prove it, we should calculate the value of the constant k, and if it remains the same for these three series, that will prove that these findings are consistent with our conclusion, which we made on the basis of these data given in the first table. Now, let's do that. For a reaction which obeys the second order, so we know the equation. Here it is, equals k times t. Let's do that. Okay, let's do that. So I will change the color. Yeah, okay. So let's calculate K1. By 1, I mean this data given in this column. We can see that the initial concentration of the reagent A is equal to 10 times 10 raised to minus 3 moles per liter. Okay. Now, from this equation, we can write that K is equal to 1 over T times, and in the brackets we write this algebraic sum. Okay, and let's plug these values into this formula. So K1 is equal, instead of T, we write 200, then C, the concentration of the reagent A at time 200 is equal 8.05 times 10 raised to minus 3 minus. Okay, so it's minus 3. For that reason, we can write 10 raised to 3 in the denominator. But in these two fractions, the denominator will be the same. We can put it here before the round brackets, and finally we got this one. Okay. Okay. So let's calculate it. So 10 raised to 3 is equal to 1,000. 1,000 divided by 200 is equal to 5. Is equal to 5. 5 here. So 5 times 10 minus 8.05 divided by 10 times 8.05 gives us 80.5. So I can make some simplifications in order to get an approximate value of K1. So 10. So if we pretend that 8.05 is equal to 8 roughly, so we can say that 10, this these brackets, what we've got in these brackets is equal to roughly 2. 2 times 5 is 10. 10 over 80 is 1 out of 8. It's roughly 0.12. But we can, I've got a calculator, yeah, and we can get an exact value. 1 second, so times 5, and we divide it by 8.5. Yeah, we've got 0.12. The number of significant digits is 2. For that reason, I round off this way. So round off this value to 0.12. Yes, this is the value of the constant, rate constant. Okay, let's take the second, the rate constant for the second findings. So 1,000 over 400. Okay. 1 second, please. Okay, minus 1 out of 10. Okay, we multiply to 5,000 and divide by 400. Yeah, again, 0.12. The same for K3. We got the following. It's 800 minutes. 1 over a fifth minus a tenth, right? Okay. It means a fifth. Oh, I'm sorry, a tenth, right? Is a tenth. A tenth multiplied by 1,000 gives us 100. Yeah, and we got so we can see that roughly, or the average value of the rate constant of this reaction is equal to 0.12. What about the measurement units? Meter? No, no, minute. No? Yes, that's it. Thank you very much. This is the first reaction. I mean to say the first problem. And I hope that it was as clear as day for you how to get that answers and how to prove that the data um, contained in the second table are consistent with the findings with regard to from the first table. Thank you. Now we're proceeding to the next problem. Here it is. So we've got a decomposition reaction where ethylene oxide decomposes, and we got the scheme of reaction because the products of the reaction are methane and CO. The whole process takes place in the gas status. Yeah, it's a gaseous reaction, and the temperature is 414 degrees Celsius. So we've got a table containing the findings of this reaction. The time is the first line of this table, and the other contains the pressure of the whole reaction mixture, and the measurement units of the pressure is torr, is the international name of millimeters of virgin in Latin, but we say these days we call it torr. The first question is to find the order and the rate constant of this reaction, and the second question is what else we should know in order to be able to determine the activation energy. So I can answer the second question immediately, because in order to get, okay, let's do it one by one. Okay, now we've got a gaseous reaction, right? In this case, I can start from the very beginning. So let me write down the scheme of this reaction this way, where A stands for ethylene oxide, B is methane, and C is CO. Okay, we've got the initial pressure of the gaseous ethylene oxide, let it be PO. Okay, and naturally, in the very beginning of this experiment, the whole system contains no traces of the products. Okay, now while the reaction is taking place, A goes in the reaction in order to get some products of B and C. For that reason, its partial pressure drops by delta P, and finally, at moment T, the partial pressure of the reagent A is equal to P0 minus delta P, right? Now, as for the products, their partial pressures are equal to delta P, both. So either of these is equal to delta P. Now, we remember that whenever we deal with a gaseous mixture, the pressure of the mixture, sigma P, is equal to the sum of the partial pressures of the components. So it means P of A plus P of B plus P of C, right? We know that at moment T, the partial pressure of the reagent is equal to P0 minus delta P, right? The partial pressure of B is equal to delta P, and the same is about the other product. It's also delta P, right? And we can say that the total pressure of the reactional mixture at moment T is equal to P0 plus delta P. In other words, as the reaction goes on, the total pressure of the system increases, and the findings are given in the table prove that. Okay, now let me rewrite it so that it can be seen more clearly. From this equation, we can write that delta P is equal sigma P minus P0. Okay, and let plug this expression here instead of delta P. In other words, we can write that the partial pressure of A at moment time moment T is equal to P0 minus, instead of delta P, we write this expression. Yeah. If we open the brackets, we will get twice P0 minus sigma P. Okay. Now, I have no idea about the rate of this reaction, and I can assume, and this approach is known as integral way of dealing with determination of the rate. So I can do it, no problem. There are no restrictions about that. So I'm writing the following: assume n equal 1. In this case, k is equal 1 over t times natural logarithm of the initial concentration of A over B T. Okay, right? That means this one. So we got the formula, and I'm going to calculate the values of K for each of these experiments. And one, two, three, four. We got 5 series. We've got 5 series of experiments carried out in order um, to collect these data. It's not a problem. And if K in each part is equal to K from another experiment, that will prove that my assumption that n is equal to 1 is not groundless. Let's do that. So K sub 1 is equal to 1 over, so T1 is equal to 9 minutes. Okay, natural logarithm. Now, the initial pressure of the system is 116.5. That corresponds to the initial pressure of the reagent. So 116.5 minus, and at time 9 minutes, the total pressure is equal to 129.4. Okay, so let me take a calculator. 1 second, please. Okay, the first value is, excuse me, 0, 0.013 minutes raised to minus 1. Okay, let's do, let's compute the magnitudes of K2 in the same manner. Now it's going to be 1 out of 13 times natural logarithm of the fraction, and the fraction is the whole denominator is the same, 116.5. The denominator is double this value minus, and at time 13 minutes, the total pressure is equal to, if I can see it correctly, 134.7. So, 1 second, please. You always need a calculator around to get the right answers. 1 second, so it's total minus 134.7. Oh, sorry, I'm in a rush, and so for that reason, I'm making some stupid mistakes. I found it 34.7. Okay, now measure the perfect. And now we divide by 13, and we got, yeah, so we got 0 0.013 minutes raised to minus 1. Yes, we got the same value, which may mean, I'm saying, I don't say that means, I say that may mean that we are still on the right track. Now let's continue computing the values of K for the other experiments. Now we are going to do this for K3. K sub 3. Okay, in this case, it's 1 out of 18 times natural logarithm of 116.5. In the numerator and denominator, double that value. Okay. Okay, minus 618, 141.3. Okay, let's do that. Minus 141.3 Mention nothing, and now we divide no 18 and do that. Okay. It's 0.013 and 3. Okay. Again, it's similar. It's close to the previously found two values. Okay. Now let's do the same for k sub 4. Okay. 15. Please, when you're writing this, um, you should make sure that you are writing this neatly and neatly writing neatly means a lot, believe me. 172.1 if I can see it correctly. Let me take how many go. So 65 over minus 172.1. Now we divide by 50, so we got, oh gosh, that's something wrong. One second, please. 0.5, okay. So we divide it minus, okay, okay. Yeah, so now we divide to 15. Oh gosh, what am I doing? My calculator has gone crazy. I'm awfully sorry for this long, long pause. It's because my cat is staring at me, trying to guess what I'm doing. Oh, finally. Yeah, it's very again, but you can see that it's very close to the previous values. Now I see for k sub 5. Okay, minus 1.2. We got minus 2.2. Okay, natural look, and now we divide 200. Yeah, we got it. It's um yeah. Now we can see that for each series of experiments, we got nearly the same value of rate constant k. Its average is roughly 0.013 minutes raised to minus 1. That means that n is equal to 1. In other words, that this reaction obeys first order. Okay. Now, we have answered these questions, right? Yeah. 1 second. Oh, I'll just open again. Something. I'm looking at the problem itself. Mhm. And we are supposed to answer the last question in this assignment, which is what else we should know in order to calculate the activation energy. Well, in order to be able to calculate the activation energy for this reaction, we need to know the same data, but for another temperature, and preferably close to this one. In this case, why am I saying close, preferably close to this one? Because in this case, within this temperature range, the temperature doesn't change a lot. And for that reason, the value of activation energy may be considered to be constant. That's it. Thank you. Let's proceed to the next assignment. Here it is. We got the regions A, B, and C, and we got a series of experiments carried out and the findings contained in the table. Well, on the basis of these experiment data, we are supposed to estimate the order of all the three reactants. And then we are also supposed to calculate the value of the rate constant K. Let's do that, and it's not so very hard to do. So let us write the general equation, chemical equation. If we have three reagents, so we can write that the rate of the process is equal to K times concentration A raised to X times concentration of B raised to Y, and the concentration of C raised to, that'll be Z, okay? Now, let's write the equations for each of the four experiments one by one in order to see which of them we can couple to um, get least procedures to calculate the values of X, Y, and Z. For the first series, we can write that it is K times the concentration of A is this one. The concentration of B for experiment 1 is 0.005 times raised to Y, and the concentration of C is 0.01 Z, and the initial rate is equal to 2.1 times 10 raised to minus 5. For the second experiment, we can write that it's K times the concentration of A is the same. The concentration of B is, let's say, the same. And the concentration of C is 0.015 raised to C, and the value of the initial rate is 3.75 times 10 raised to minus 5. So it's not convenient to couple these two equations with each other. To be more specific, we will divide term by term equation 2 by equation 1, and these will cancel each other. The first three terms will cancel each other because they are the same. And so let me write down that will cancel each other, cancel, and finally we got 0.015 over 0.01, and this fraction raised to Z is 75 over 2. Let me make a calculator. So we got 1.5 here. 1.5 raised to z is equal to 3.75 over 2.5. That's it. This is 1.5 for that reason. Z is equal to 1. We have just calculated, we have just estimated the order of fraction with respect to C. Okay. Okay. Now let's do a similar thing for equation 3, for example. It's k times the concentration of A is 0.1 x. Okay, the concentration of B is the same raised to y, and the concentration of C is also the same. But this time I don't need to write Z because I just calculated it. And the initial rate is equal to 10 times 10 raised to minus 5. Okay, let's see what I can do here. X. Yeah, let's divide the third by the second. Yeah, okay, let's do that. If we divide the third by the second, we will get k. These two k's will cancel each other. This term is absolutely the same as this one. They will cancel each other, that's why. But these aren't. So uh-huh. Um, this concentration of C, and this is the concentration of C for the second experiment, and Z is equal to 1. 10 over 3.75. Okay, okay. So that means that equals 2 raised to y is equal. Let me take calculator. 10 is equal to 4 or 2 squared. For that reason, y is equal to, oh, so we have just calculated that the order of reaction with respect to B is equal to 2. Okay, good. Now, all we need to do is just to calculate the value of X. We can do it easily using either of the three equations. Let's take the first one, for example. No, again, we need a couple of the first. Let's take the fourth, no problem. Let's write down the kinetic reaction for the fourth experiment findings. So K times 0.02 times X 0.0005 squared, because this is 1, and times 0.01, and that equals to 2.5 times 10 minus 5. Okay. Now, if I can substitute, for example, the 4, or better say the third to the 4th. Yeah. If I not substitute, if I divide the third reaction by the fourth reaction term by term, so we will get a nice thing, I guess. So for the third reaction, it is, so let me write down here. So the third reaction divided by the fourth reaction. So what will we get? Okay, K times 0.0 x times 0.01 squared times 0.01. Now the fourth K times 0.02 x 0.005 squared times 0.01 for the third reaction. I mean, for the third experiment, I'm sorry, the rate is equal to 10 times 10 to the minus 5. And for the fourth reaction, it's equal to 2.5. Okay. 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 So finally, we've got the following. And second place is 4. We've got 1. And that means in the ranking that x is equal to 0. Okay, now we got all the uh, orders with respect to all the 3 reagents. And we can write that the rate of reaction is equal to K times uh, the concentration of B squared times concentration of C. Here it is. Now we can calculate the value of K. Let's do it from the first experiment data. So K is equal W divided by concentration of B squared times concentration of C. The concentration, no, the value of the reaction is 2.5 times 10 to minus 5 over the concentration of B is 0.005. Oh my God. Squared. Again, something wrong with my writing because I'm just going to the computer. Okay. And 0, 0, is 1 and C is equal to, that means 100. So the value of K is equal to 100. Yeah, that's it. Again. Oh, thanks God, it has returned. It has returned. So it equals to 100. If you plug in all these, if you plug in all these values, you will get 100. That is the answer, and we have just calculated the value of the orders with respect to the 3 reagents, right? And also the value of the constant of the reaction, which is exactly 100. So this is the end of this want to say reaction. This is the end of this problem. Thank you. Thank you. Mhm. Yeah. Now we're going to continue our work, and here's the next problem. We got the reaction of thermal decomposition of neutral chloride, which obeys the following stoichiometric reaction unities. Well, using the following data, we need to find the order of this reaction, and also we are supposed to calculate the time when the partial pressure of natural current falls by 60% of the initial pressure. As you can see, the initial pressure is equal to 90.9 torrs. Okay, let's start from determining the order. I'm going to use the integral method, which starts from the assumption. And my assumption, my first attempt of the assumption is assuming that the order of this reaction is equal to 1. So maybe which color should I? Right. So assume the first order of the reaction. Okay. Now, if I let me rewrite the schema of the reaction this way, it's more convenient. Okay. So we've got the initial pressure of natrium chloride, yes, and no trace of the two products in the mixture in the beginning. Delta P is the drop in the partial pressure of the reagent A, and finally you got the initial, I'm sorry, the partial pressure of the reagent A, which is equal to P0 minus delta P. Okay, then delta P is the partial pressure of product B, and delta P divided by 2 is the partial pressure of the product C. The total pressure of the mixture is, as according to Dalton's law, is the sum of the partial pressures of all the participants of the reaction. It's P0 minus delta P, that's for PA, plus delta P, that's for P of B, and plus 0.5 times delta P, that's for partial pressure of the product C. In other words, sigma P is equal to P0 plus 0.5 times delta P. Yeah, it is right, because we can see that the total amount of the substance of the products is going up. For that reason, the pressure goes up as well. And we can see that. Let's take delta P from this expression. So delta P is equal sigma P minus P0, and that is doubled. Yeah, okay. Now we can, it means double sigma P minus double P0. Okay, but we are working with the reagent A. At any time t, the partial pressure of the reagent A is equal to P0 minus delta P. And so the delta P, we plug in this expression minus the double sigma P minus double P O. And if we open the round brackets, we will get 3 times P0 minus 2 times sigma A. And we should come back to the point when I assumed that the rate of the reaction is equal to 1. For that reason, I assume that the kinetics of this reaction follows this equation. Return to. So this is the final formula, which enables me to calculate the magnitudes of K for experiments 1, 2, 3, and 4. And if these values turn out to be close to one another, that will prove that my assumption that n is equal to 1 is correct. Let's do that. So K sub 1 means that we are going to do the calculations related to the first experiment. K sub 1 is equal to, the time is equal to 300, and we're going to write it in the denominator, right, times natural logarithm. The initial pressure is 19.9 torr. Here 3 times 19.9 minus 2 times, and is 21.7 torrs at the time of 300 seconds. So let me calculate. I'm sorry. With a copy because oh, I've got a few. For that reason, I have a wonderful French pronunciation. Mention that please, and then we do actually benefit on it. We got 6.65 times 10. Rest is 4 minus 4 seconds raised to minus 1. Okay, let's do the same for K sub 2 is 1 out of 900. Minus the pressure of the system is equal to 24.4 at this time. Oh, sorry. Double. Okay, okay, okay. We got 6.69 times 10 to minus 4 seconds. 2 minus 1 is very close to this one. It means that we are probably standing on the right tracks. Yeah, let's do this calculations for K sub 3. Okay, it's 19.9 over 3 times 19.9 minus double 26.3, and one second please, 19.9 3 times 19.9 minus 2 times 6.3. Yeah, it's 6.87. 6.87 times 10 to minus 4. Again, very close, and that's good. It's a good sign. And last one, K sub 4. Okay, 2000. Okay, 3 times 19 minus 2 times 27.3, right? On the second place. Which will be only divided to 1000, yeah, 6.81, 6.81 times 10 raised to minus 4 seconds per seconds in minus 1. Okay, we can see that all the k's we have just calculated are very close to each other, which tells us only one thing, that our assumption that n is equal to 1 is correct. And now we need to calculate the average. So the mean of k is equal to sum of the k's found divided by 4. Because we got totally 4 values. Let me do it. So 6 point 61 is for the first, plus 6.61 is for the second, plus 6.87 for the third, plus 6.81 for the fourth, and then we divide by 4, we get 6.76 roughly. 6.76 times 10 2 minus 4 seconds, 2 minus 1. This is the value of the average rate constant for this reaction. First of all, we have calculated the value of the rate constant of this reaction, and also we have proved that the rate of this reaction is equal to 1. And now, having found the value of the K, we can answer the question related to the time when the partial pressure of the reagent, hydrochloric, falls by 60%. Let's do that. So we're going to use the same formula, but this time we need T, right? We can write that T is equal to 1 over K times the logarithm of A over PT of A. But we know that the final that if the value of the partial pressure of this reagent is 60% of the initial, right? That reason that you write the K, we can plug in this value. Is 76 times minus 2 minus 4, like we have 1 is 1.6. Yeah, okay, let's do that. We can substitute it easily with our calculators. So, and yeah, it's equal to 755.7 seconds. So after 755, okay, maybe 756 seconds, the pressure, the partial pressure of nitric chloride will drop by 60%. This is the answer for this question. Thank you. I'm not sorry, I have forgotten to take a look at the problem itself. I think that it's got a continuation. It's part B. Let us take a look at part B of this problem. Here it is. In part B, they ask us if the following data given in this table are concordant results with A. So in order to answer this question, all we need to do is just to calculate K's for each case, and if K is close to the one which we have just found, we have calculated it in part A. In this case, the answer is positive. Let's do that. Again, remember that the rate of reaction is equal to 1 for that reason. We can write that the rate of reaction is K times the pressure of the substance raised to 1. In other words, just K times P. For that reason, we can write that K is equal to W over P, right? For the first, we can write that K is equal the initial, so 0.96 times 10. This factor is 1,000. For that reason, we should divide 0.96 by 1,000. Okay. And we divide by the initial pressure of this reagent, which is 1.45. And in this case, let me take a look. 0.96 times 10 to minus 3. Okay. We divide by 1.45, and we got 6.62 times 10 raised to minus 4. It's very close to what we got from the previous. Yeah, K2. 2.23 times 10 to minus 3 divided by 3.39. Let's take a look. I mentioned this. It's got it's equal to another very close magnitude, which is equal to 6.59 times 10 to minus 4. Very close indeed. A sub 3 for this column. So it's 4.06 times 10 raised to minus 3 divided by 6.17. Okay. Yeah, 6.58 times 10 to minus 4. Another close value and insert 4. Let's take a look. Yeah, it's 6.54 times 10 to minus 4. First of all, they are close to each other, and secondly, each of them is close to the mean value of K, which we got in the solution for part A, which that means on the one thing that these data are okay, so they agree with the results we got from the solution of part A. That's it. Now that's all. Now we'll proceed into the next problem. Here it is. We've got a reaction of dimerization when 2 moles of A transforms into a mole of 2 atomic molecule A2. And these chemical reaction occurs at the temperature of 400 Kelvin. And we've got a table showing the findings of this experiment. We've got the change in the total pressure of the whole system in time. They want to calculate, they want us to calculate the rate of the constant and the half-life. Let's do that. So they give us the key to start from, that this is the direction of this of second order. Okay, and that of course greatly makes our work much easier to deal with, because we don't need to prove that this is a second order action. However, we could guess it because of the coefficient 2, which stands in for a in the schema direction. Anyway, we know the formula. K is equal 1/2 times, in brackets, we got this expression. However, we will guess for that reason, instead of C, we can write P, because concentration is proportional to pressure. And we can write that it's equal 1/2 times 1P of A at time T minus the initial pressure. The initial pressure can be seen from the table is equal to 645. As for P of A at time T, so this is something which we're going to deal with at this moment because it's not clear. So let's rewrite the schema of the reaction. In the beginning, we got P sub 0 and no trace of the product A2. During the time T interval, we see the drop in the partial pressure of A is delta P, and still nothing changes with the product because it's not a unit yet, and the P of A at time T is equal to the initial pressure of A minus delta P, right? The initial pressure minus delta P. This is what the partial pressure of A is equal to at time T. As for the product, its partial pressure is equal to delta P halved. According to Dalton's law, we can write that the total pressure of the whole system, sigma P, is equal to the sum of the partial pressures of A and A2, the product, which means that it's equal to P0 minus delta P plus 0.5 times delta P. And from this expression, we can express delta P. Delta P is equal P0 minus sigma P reverse. That means 2 P0 minus 2 sigma P. Okay, and now we can plug this expression instead of delta P into this formula. So P of A at times T is equal to P0 minus double P0 minus double sigma P. Again, by sigma P, I mean the pressure of the whole system at time T. That means if it open the brackets, okay, and now we can substitute P of A at time T with this one. That means that K equals 1/2 250 times double sigma p minus p0 minus 1 p0, which means p0 minus double sigma p plus p0 double PO minus double sigma P. We put 2 out of the around brackets. T times P0 times double sigma P minus P0. So that's the formula. Okay. And now we can calculate P1 for this set of findings. Experiment 1. 2 times 645 minus 561 divided by t is equal to 15. P0 is 645. 2 times 561 minus 645. So let's do point 47. Okay, I'll get first is 1.09 times 10 raised to minus 1, 2, 3, 4, 5. That's the first one. Then case of 2 is equal is equal to 2 times 645 minus 476 over 115 times 645 times 2 minus 476 minus 645. Okay. We got 1.1 times 10 minus 5. Good. Then let's do the same for case sub 3. It's 2 times 645 minus 436 divided by 250. um, 645 two times 446 minus 645 minus this. That equals 1.1 times 10 raised to minus 9. Now, case of 4. Okay, and this 412 divided by times equal to 350 times 645 and 512 minus 645. I'm writing this in one line in order to minimize as much space on the screen as possible. Let me uh, take the writings from concept of place 645 minus 412 and doing down 350 by 645 and minus 645. Right. Again, we got 1.15 times 10 raised to minus 5. And base of 5 is go. Let me do it without writing the intermediate expressions. So 645 minus 390. Okay, then we double it and divide by the time which is equal to 500. We got 1.17. 1.17 times 10 raised to minus 5. As we can see, all these values of k are very close to one another, which means that indeed this is a rational of second order, and the average is equal to the sum of k's divided by 1, 2, 3, 4, 5. Let me do that. So 1.09 plus 1.1 plus 1.15 plus 1.17, and we divide it by we got 4.9 times 2 to raised to minus 5. Okay, that be so. We have just calculated the rate constant. Okay, yeah. Now, what we need to do is just to calculate the half-life time. let's do that. First of all, let's write the formula. The formula is that would be like this. So K is equal 1 over tau. B is equal B0 multiplied by half minus 4P0. And that means that tau is equal 1 over K 2 minus 1 1. So P0. Okay. So we've got a formula. We've got a formula. Okay. Okay. It means that what we have just calculated K is 0.9 times 10 raised to minus 5. The initial pressure is equal to 645. Let me take my calculator. It's 172 point 3 seconds. So we have just calculated the first half time, and now we need to calculate the second half time. And what does it mean, the second half time? That means that this time we take the half of the initial pressure. In this case, it's equal to 0.9 times 10 to minus 5, 445 halved. Let me take a calculator. In second place. So time. Okay. It gives us 345 seconds. 345 seconds. That's it. As we can see, the length of half-life depends on pressure. That's it. So second half life is larger than the first half life, and it's because the order of the reaction is this is second. That's it. Thank you. I hope that you're ready to proceed to the next problem. It is interesting because it shows the influence of a catalyst and its participation in the process and in the final kinetic equation. So we've got the reaction N2O decomposes into molecular nitrogen and oxygen, and this reaction is catalyzed by molecular chlorine, and the rate of the reaction is found to be dependent on the partial pressures of the reactant N2O and the catalyst Cl2 or chlorine, molecular chlorine. And we've got findings obtained from 3 experiments where we can see the dependence of the initial rate on the partial pressures of N2O and chlorine, and we are supposed to estimate the order with respect to N2O and chlorine. So actually, we have done we have dealt with a similar assignment before, and we are going to apply the same technique. So we can write that the initial rate of this process is equal to the rate constant K multiplied by the partial pressure of N2O. Let's put it as A, and this pressure is raised to X times the partial pressure of chlorine, let it be B, raised to Y. We are supposed to find the values of X and Y. So let's do that. Let's write the first kinetic equation based on the findings obtained from the first experiment. So the rate constant multiplied by the partial pressure of N2O, which is equal to 300 torrs raised to X, times the initial the partial pressure of chlorine is 40 times so not times, raised to Y, and the initial rate is equal to 3. 3 initial rate. Yeah, okay. It's torques per second. Torques per second. Okay. Now we can do the same for the second series of experiments. So we can write K times 150 raised to X times 40 raised to Y, and that's equal to 1.5 torques per second. And we can already see how much X is if we divide 1 by 2. We will get the following. And so, this equals to 2 raised to X, and that is 2. But the reason X is equal to 1. We have just found the rate with respect to N2O. Now we can find Y. So let's write the equation for the third experiment. K 300 x 300 raised to X times 10 raised to Y is equal to 1.5. Okay, now we can divide 1 to 1 by the third equation term by term, and we will get the following. For the third is 9.5. Okay. Cancellation. So we got 4 raised to Y is equal to 2. That means that Y is equal to a half. And now we can write a complete kinetic equation for this reaction. Okay. Yeah. Also, for the temperature at which this series of experiments were carried out, we can calculate K. We can calculate K. Well, actually, we can do. It's not asked to do in this assignment, but anyway, we can do that. K is equal the initial rate divided by these two terms raised to the corresponding degrees. So let be 3 if we take the findings from the first experiment. So the pressure of N2O is equal to 300. It's 40 square root of 40. So let me give it 2 square root of 40 is 6.32 times 300. Okay. So it's 1.85, 1.8, I'm sorry, 1.58 times 3 raised to minus 3. That's it. That's it. Okay. This is the solution for the solution to this problem. So We are going to do with the last uh, assignment, the last problem. Um, I'm going to say out what is given in this problem. We've got a reaction between liquid toluene and dissolved chlorine and 170 degrees Celsius. This reaction is catalyzed by acids with a catalyst concentration of 0.117 moles per liter. The reaction was followed by analyzing for chlorine, and these findings are shown in the following table. You're going to see this table right now. Here it is. So we can see the dependence of the concentration of molecular chlorine with in time. So they ask us to determine the rate of this reaction and to calculate the rate constant. So let's do that. Again, let's assume the first rate of this reaction, which means that if we finally get a series of values of k at the assumption of n equals 1. So, and if these values are equal to each other or very close to one another, so that will prove that the assumption is correct. Let's do that. Okay. The initial concentration of chlorine over the concentration of chlorine at time t. Let's do that. So K sub 1 is equal to 1 out of 3 times natural logarithm of the initial concentration of molecular chlorine is 0.0775 divided by 0. Oh, again. Oh gosh, it's not writing again. Oh, thanks God it's back. So divided by 0.0565. So let me take a calculator to get the number. So the numerical value. So it's 0.105 minutes raised to -1. Okay, let's do the same with case of 2. Now it is 1 out of 6 times natural logarithm of 0.0775 divided by 0.0410. In second place. We got 0.1061. Actually, it's very close. A sub 3. And we divide by 0.0165. Okay. And we divide by 10. It's again very close. It's 0.1073. And the last case of 4. is 0, 0, 10, 63, very close. Um, so as we can see, k sub I remains constant. For that reason, we can assume that n is indeed equal to 2. It's a fraction of second order. Oh, I'm sorry, first. Sorry, first order. And the main value of the rate constant is equal to the sum of the k's just found divided by 4. What is this? Plus, plus, plus. No, we got it. It's 0.1063. You got four numbers, 4 digits after the point. That's why we round off this value the same way. Okay, we've just got the numerical value of the rate constant of this fraction, which is equal to 0.1063 minus raised to minus 1, and the order of this fraction is equal to n. This is the first part of this problem. And now we're going to proceed to the next one. What is it, please? Okay. Oh, it's gone. Where is it? Let's see, please. Hold on a second. Yeah, okay. We got another table. New teams is the dependence of the concentration of a catalyst and dependence of the concentration of the catalyst and the effective rate constant k prime. We are supposed to determine the order with respect to catalyst, and k prime are found, and put into the table. Oh gosh. We should use the following results to determine the order with respect to catalyst. The value of k prime quantitative found as above. Okay, as above or as below? It's a good question. Okay. So let's take a look. So we need to find to determine the rate with respect to the catalyst. My brain is working well now. Okay, let me take a look. So, I guess the following it's K prime, not capital, but um, volume concentration of chlorine, where K prime is simple first order rate constant. In turn, K prime is equal to a double prime times the concentration of catalyst raised to n. In turn, K double prime is equal to K times the concentration of toluene raised to n, and the concentration of catalyst raised to n. But we need this, and I guess this. So if we check natural logarithm of both parts of this equation, we get the following. Natural logarithm K prime is equal to natural logarithm of theta prime plus n times natural logarithm of the concentration of catalyst. Okay, and we need to find a right. Okay, now let's draw a simple chart. Natural logarithm of the concentration of the catalyst, and here the natural logarithm of a prime. Now I need a calculator. Roughly -3 is natural calculator, a natural logarithm of this. Minus 358 minus 2.59 minus 2.94 minus 2.30 minus 2.41 minus 1.88 minus 1.76. The logarithm of this is minus 1.61 minus 1.31. Okay, and now I should draw the line in order to see the value of n. is going to be a slope of this line. Oh, hold on a sec. Hold on a sec, please. I'm opening Microsoft Excel. Okay, okay. Minus 3.82. So minus 3 minus 3.58. The next minus 259. Two 59 minus 2 minus 94. Okay. Then 230, 241. Okay. Next minus 1.88. Seven 61 and minus 1.31 minus 1.31. Okay, on the second place. Um, Now we're proceeding to the Excel. I have just put down the data. And I'm going to draw a line. Oh, we got line. Yeah, okay. It's perfectly well straightforward and uh-huh. It's 1.6. As you can see, the equation of this trend is shown on the diagram. And we can see that n is equal to 1.6. Is 1.6. We can write that n of catalyst is 1.6. This is the answer. Thank you very much.